Chairman and ladies and gentlemen, good morning. Mass spectrometry is a highly versatile analytical technique that can be applied to investigate tissue and biofluids for molecular fingerprinting. Conventional mass spec workflow involves sample ionization, separation of constituent ionic species according to mass-to-charge ratio, detection of a focused beam of separated ions, and spectral representation. Here, the positions and intensities of peaks in the resulting spectra correspond to particular biomolecules and their relative concentrations, respectively. Recent advances in this field have led to the development of imaging mass spectrometry, or IMS, an approach that allows direct, non-destructive mass spec profiling of intact tissue sections. With this technique, ionization is applied directly to the tissue surface across a predefined array of coordinates, each of which then generates its own unique, spatially localized mass spectrum. Seems to be a problem. The major strength of IMS lies in its ability to measure chemical activity with direct correlation to morphological features of interest, bypassing the need for time-consuming steps such as laser capture microdissection. In very broad terms, IMS approaches are likely to have two main areas of application in systems oncology. Firstly, they offer a means of chemically mapping the tumor microenvironment in a way that has not been possible until now. This has potential to generate novel prognostic and therapeutic cancer biomarkers based on region of interest-specific molecular ion composition. Secondly, IMS approaches offer a means of assessing the localization and concentration distribution of chemotherapeutic agents and/or their downstream metabolites within different regions of the cancer microenvironment. This in turn offers the opportunity to explore anti-cancer drug mechanisms and efficacy from an entirely novel perspective. IMS approaches have yet to realize their full potential in cancer research, and there are currently two fundamental barriers hampering effective translational application. Firstly, effective methods for precise correlation of histological features with IMS-derived biochemical signatures are lacking. Currently available methods rely either on naked eye visual assessment and comparison or very basic fiducial marker-based systems for image co-alignment. These methodologies are not fit for purpose in this context, especially where the aim is to biochemically profile very fine histological details. Secondly, the IMS analytical pipeline is highly complex. Data pre-processing, image co-alignment, region of interest feature extraction, and multivariate analysis are all critical prerequisites. And currently, there are no intuitive, user-friendly platforms capable of addressing all of these requirements in a clinician-friendly way. The specific aims of this study, therefore, were firstly to develop a precise method for image co-registration to allow accurate correlation of histology to IMS-derived biochemistry. Secondly, we've sought to develop from scratch an intuitive software interface capable of addressing all requirements along the IMS analytical pipeline. Finally, we've sought to apply the devised methodological framework to investigating region-specific molecular ion patterns within the colorectal cancer microenvironment. Samples of fresh colorectal tissue for this study were acquired from 49 consenting adult patients over a one-year period. These were sectioned to 10 micrometer thickness before being subjected to desorption electrospray ionization, or DESI, imaging mass spectrometry. This involved using an in-house thermo-exactive mass spectrometer equipped with custom-built DESI ion source. Spectra were acquired in the 200 to 1,000 mass-to-charge range, and sections were H&E stained and digitally scanned at high resolution post-DESI analysis. The novel image co-registration methodology that we've devised and implemented here operates using an in-house designed Euclidean image transformation algorithm. Essentially, this relies on scaling, rotation, and multiple image translations to create a precise pixel-to-pixel match between the non-aligned template H&E image and the reference IMS image. This short video clip shows our image co-registration toolbox interactively in use. It's supposed to start automatically, but... So here I'm just setting the transformation parameters And then at the bottom right, you can see warping of the optical image such that you get this precise pixel-to-pixel matching with the corresponding IMS image. I can preview the match, and in this case, it's very strong, so we can move on to the next stage of the analysis. Sorry, this is not working for some reason. We've gone on to develop a novel, all-in-one intuitive interface for IMS data mining and interrogation. This allows the user to perform robust data pre-processing, image co-alignment, region of interest feature extraction, and multivariate analysis as an all-in-one package. Currently, nothing as sophisticated as this exists elsewhere to our knowledge. This next video clip shows our intuitive data mining interface in use. This can be performed by the histologist, which is why we've designed it like this. Here I'm selecting regions of tumor in red, and you get automatic co-selection of corresponding pixels in the matched IMS image. Here I'm selecting in green some regions of tumor microvasculature, and also in blue some tumor-adjacent stroma with automatic co-selection of IMS pixels. You can then intuitively subject these data points to multivariate analysis, as we have done here, and we're getting excellent separation and clustering of data points according to tissue type. Here I've focused in on the blue, which is the stromal profile specifically. In terms of chemical composition, IMS profiles of the colorectal cancer microenvironment revealed predominantly complex structural glycerophospholipids, including, but not limited to, phosphatic acids, phosphatidylcholines, and phosphatidylserines. We've observed significant differences in the abundance and localization of these molecular species according to different tissue regions in the microenvironment. We've gone on now to use this data across the entire sample set of 49 patients, including 180,000 spectra, to populate what we've referred to as a histologically authentic chemical database. This should allow novel sample-to-sample comparison based on region of interest specific molecular ion patterns. To illustrate this point, this is some interesting preliminary analysis that we've performed looking just at decistromal profiles according to lymph node status. The striking feature here is the excellent separation and clustering of samples based on stromal lipid biochemistry and according to lymph node status, and this has significant translational potential. To conclude, IMS approaches offer an additional layer of spatiochemical information to supplement conventional histopathological strategies. We've identified unique region-specific molecular ion patterns within the colorectal cancer microenvironment, and these have potential to generate next-generation cancer biomarkers. Specifically in this study, we have comprehensively addressed the two major roadblocks currently hampering translational IMS efforts. We've developed an entirely novel method for precise image co-registration, and in addition, we've developed from scratch an intuitive software platform to cover every aspect of the IMS analytical pipeline. Concurrently, we've begun construction of a first-of-its-kind histologically authentic chemical database, which will allow novel sample-to-sample comparison based on region of interest-specific molecular ion composition. Thank you.